All right, 4, 5, 5, we have complex numbers. Our objectives then are to graph complex numbers. That'll be a fun one on a complex plane. So a different plane than we're used to using, but very similar. We're going to find the absolute value of complex numbers. We're going to simplify powers of I. Remember, I is an imaginary number. We're going to add, subtract, and multiply complex numbers. And last but not least, solve some real-world applications involving complex numbers. Okay, so let's look, let's see if we can make some sense of our chart here first, right? We've had this for our whole numbers. Earlier this, well, as a sophomore in geometry, we talked about the whole numbers, or the integers, the natural numbers, counting numbers, rational, irrational numbers, had a similar graph. So this one is complex numbers, which are made up of A plus BI. Okay, are complex numbers. Within the complex frame of numbers, we have imaginary numbers, which are A plus BI, where B is not equal to 0. So notice we have -2 minus I, 3/5 minus 9I, 6 plus I times the square root of 2, 3 plus 4I. These are all imaginary. Okay. Now, inside those imaginary numbers, we can also have pure imaginary. And this is when we have 0 plus BI. So we don't have our A value, it's not that we don't have one, our A value equals 0. So we don't have one. So pure imaginary numbers are like -7I, I, 9I, 3I. Okay, they don't have the plus sign or a minus sign in there separating them. Now, the real numbers, which is what we've always broken down before, is when we have A plus 0I. So this means we don't have an imaginary component. This is our whole numbers, our counting numbers, our rational, irrational. All of those numbers fall here in the real numbers. Okay, and we could dig deeper into this from what we studied in Algebra 1 and geometry. But our focus is really imaginary, and then realizing all of these are actually called complex numbers. Okay, so our complex numbers, which is represented with a lowercase z, is a number that can be expressed in the standard form z equals a plus bi, where a and b are elements of the real numbers, and I is equal to the square root of -1. An imaginary number is a number in the form of a plus bi, like I said, where b does not equal 0. So we have an imaginary component. In a pure imaginary number, it's in the number of a plus bi, where a does equal 0. We don't, in a pure imaginary number, we don't have a real number component. Okay. All right, so complex numbers can be graphed in the complex plane. The complex plane is similar to the Cartesian coordinate plane that we use all the time, but the axes represent the real and imaginary components of a complex number. So if we look here on this plane, notice our x-axis represents the real component. The vertical axis, or the y, represents the imaginary component. So if we have this number, -3 plus 2i, okay, this is our real component here. The first part is the real component. So on our coordinate grid, or our complex plane, we go back 3, -3, 1, 2, 3. And then our other part is a positive 2 imaginary. So we go up 2, 1, 2 on our imaginary, and we graph that. Now, the distance from there, because absolute value is distance, the distance from the origin to that position is equal to the square root of 13. Okay. So pretty cool stuff there. All right, so that's what this is saying, right? When we have z equals -3 plus 2i, we're going to graph the real component along the horizontal axis, because that's the real axis. We graph the imaginary component along the vertical axis, the y, because it's the imaginary component. Okay, I might have should have done that before I moved. I should have moved up before I graphed that, but that's okay. So the absolute value of a complex number. Okay, so let's go back. When we have this z equals a plus bi, which is also called the modulus, is the distance from the origin to its graph in the complex plane. Okay, it's its distance. Distance is always an absolute value. So we find the absolute value of z, our complex number. We put absolute value signs around our complex number, and then we can find what's the absolute value of a squared plus b squared. Okay, that's how we can solve it. This is going to be helpful to find out, to get from here to here. Okay, so to do that, to get from here to here, we're going to use this formula. We're going to take, well, the absolute value of a squared plus b squared. Pardon me, the absolute value of the square root of a squared plus b squared. All right, our a here is -3, so it's going to equal the square root of -3 squared plus our b squared. Notice we don't want the bi, we just want the b value. That is 2 squared. Okay, so this is going to equal the absolute value of the square root of -3 squared, which is 9, plus 2 squared, which is 4. So it's the absolute value of the square root of 13, which is the square root of 13. Okay, because it's absolute value or distance. So we're keeping it, and distance cannot be the negative. It's not going to be plus or minus the square root of 13 because it's distance. It has to be a positive. Okay. Now, let's look at the examples. See if we can get some stuff there. Graph and find the absolute value. So in A, remember, so we have 4 minus I. This is our real component, okay, 4, and I, negative I is our imaginary component. So we're going to graph a positive 4. We're going to go over 4. 1, 2, 3, 4. And then we have negative 1i. So we're going to go down 1 and graph that. That is our graph. Okay. Now, so we went, we could put the marks on here, right? We went over 4 and down negative 1i to get that point. Okay, so now we need to find the absolute value. To find the absolute value, we're going to find the absolute value of a squared, sorry, the square root of a squared. A is 4, so the absolute value of 4 squared plus b squared. Our b is the negative 1. So negative 1 squared. Okay, and let me finish my absolute value sign. So this equals the absolute value of the square root. 4 squared is 16. Negative 1 squared is 1. So this is the absolute value of the square root of 17, which is the square root of 17. So this distance, the origin, 2, 4 minus I, is equal to the square root of 17. That's what we're finding, is the absolute value or the distance. Woohoo! Got that one? All right, let me erase some of this work over here that I did and took up all the space I might need. All right, and let's graph this b here. So for b, we have negative 2 minus 3i. Okay, so let's graph it first. So negative 2 is our real component. So we're going to go negative 2 this way. And then negative 3i. So on our imaginary component, we're going to go down 3. 1, 2, 3. So there's negative 3i. So here is our position, our graphed point. And then we need to find our absolute value, or which is that distance from this point, negative 2 minus 3i, to the origin. All right, so we're going to find the absolute value of the square root of a squared plus b squared. Okay, so the absolute value of a squared, negative 2 squared, plus our b is just the negative 3. We don't want the I squared. So the absolute value of the square root, negative 2 squared is, excellent, 4, plus negative 3 squared is, very good, 9. So this equals the absolute value of the square root of, good, 13. Which means that the absolute value of the square root of 13 is just the square root of 13. So this distance here is the square root of 13. Which notice it's the same distance, right, as here, as a negative 3 plus 2i has the same distance as negative 2 minus 3i. They have the same absolute value. All right, excellent. Great job finding the absolute value of a complex number. All right, then we're going to add or subtract. Talk about adding or subtracting complex numbers. And you're going to love this part. It's really easy. To add or subtract complex numbers, we are going to add or subtract the real components, then add, subtract the imaginary components. Okay, it's just like combining like terms. Okay, so here if we have z equals a plus bi and w equals c plus di, we're going to add the real components, so the a and the c together, and we add the imaginary components, the positive bi and the positive di together. That's it. So sometimes, like if we looked at like stacking them, right, we have 3 plus 2i plus 5 minus 4i. You could look at it that way, right? 2i, positive 2i minus 4i is going to give you a negative 2i. 3 plus 5 is 8. So you have 8 minus 2i. Pardon me. Or you can group them here. Like I have a 3 plus 5 is 8. And then a positive 2i and a negative 4i is negative 2i. However you want to look at it. I prefer the combining like terms idea, this red and purple, versus having to rewrite them and stack them. Okay, on B, the thing to note is you have a minus sign. So make sure you're subtracting, or if you want to distribute this, right, and rewrite them, you could have 5 minus 3i minus 2 minus 6i. However you want to do it, that's okay. Again, combining like terms. 5 minus 2 is 3. Negative 3i minus 6i is negative 9i. Ta-da! You just subtracted and added complex numbers. Good stuff. Now let's talk about multiplying complex numbers. To multiply complex numbers, we're going to apply the distributive property or FOIL method, whichever one we need. Write the result in standard form. Remember that standard form is a plus bi by combining like terms. So you still have to combine like terms. The last thing, we're going to substitute negative 1 anytime we have I squared. Okay, because I squared is equal to negative 1. Remember, because I is equal to the square root of negative 1. Pardon me. Which means I squared has to equal negative 1. Okay, so example 3, we just need to distribute. Right, we're going to take this 5i and distribute it. So what's 5i times 3? Perfect, 15i. And then what's 5i times 2i? Excellent, it's 10i squared. So now I have an extra step because I have an I squared. So this is 15i plus 10 times negative 1, which simplifies to be 15i minus 10. 15i minus 10 would be it. Or you could also, this is not standard form though, right? It says write it in result in standard form. We need to change that to be negative 10 plus 15i. That is actually standard form. Okay, not this one. crossing it out, but I want to keep it. Okay, on B, we need to FOIL, right? Because we have two binomials that we're multiplying. So first, 4 times 2 is, excellent, 8. Last, 4 times 3i is, good, positive 12i. Whoop, there we go, positive 12i. Inside, so negative 2i times 2 is, good, a negative 4i. And last, negative 2i times 3i is, excellent, a negative 6i squared. This is our 12. Okay, so combine like terms. We've got a positive 12i, a negative 4i. So this is going to be 8 plus 12 minus 4 is 8i. The other thing we need to take care of is this is an I squared. So it's minus 6 times negative 1. That's going to give me 8 plus 8i. Negative 6 times negative 1 is a positive 6. Now suddenly I have more like terms, right? I have an 8 and a 6. So 8 plus 6 is 14. So now I have 14 plus 8i. And that is in standard form, right? A plus bi. So I'm good here. 14 plus 8i is multiplying. So the 1, this is when we just distribute, and b is when we have to FOIL. Okay, let's clear that and move on to example 4. Okay, the sum of squares. Okay, looking for these patterns. When we have the sum of squares, a squared plus b squared, factored into a product of complex conjugates, pardon me. A squared plus b squared equals a plus the quantity a plus bi times the quantity a minus bi. Okay, so when we have the sum of squares, but we're talking about complex conjugates, okay, we can have these as complex ones as well. So in example 4, we want to multiply the quantity 3 plus 5 I times the square root of 2 times this quantity 3 minus 5i times the square root of 2. Okay, so this is going to be a sum of squares. When we have complex conjugates, it's going to equal a sum of squares. Okay, we can walk through that and do it and see, but it's pretty awesome. Okay, so we would have to FOIL here. All right, so 3 times 3, the first would be 9. Outside, 3 times a negative 5i, right, is going to be negative 15i times the square root of 2. And then the inside, it's going to be a positive 15i times the square root of 2. And the last is going to be a negative 25i squared times the square root of 2 squared. Yikes. Yeah. Okay. So we have combining like terms, right? But these cancel because we have a negative and a positive, so they just cancel. So then we've got 9 minus 25. I squared is equal to negative 1 times negative 1. And then the square root of 2 squared is 2. So 9, a negative 25 times negative 1 is positive 25. And then positive 25 times 2 is 50. So 9 plus 50 equals 59. Okay, so that's the long way of doing it. We can take the shortcut and see the pattern and recognize, okay, this is the same thing as a squared plus b squared. All right, if that's the case, my a value is 3. So it's going to be 3 squared, okay, plus b squared. My b value is 5i times the square root of 2 squared. And I just realized I have this cubed. Oh my goodness, and it's supposed to be a 3. What am I doing? All right, so 3 squared is going to simplify to 9 plus, and like I said here, we have 25 I squared is -1, and the square root of 2 squared is 2. Time out. What did I do wrong here? Oh, I don't put the I in there. Of course I don't put the I in there. So I don't need the I in there. Sorry. So 9 plus 50, which is 59. All right, I'm going to have to erase a little bit there so I have some room to work my next one. So let's clear that. Okay, so let's look at example 5, where we're actually factoring this time. So we have x squared plus 4. Okay, so this is still a sum of squares, right? We see the square, x is squared, 4 is a perfect square. Okay, so we would break this down into a plus bi. So this x is our a value, b4 is our b value? No, right? Because it's squared. These are supposed to be squared terms. So this would be 2 squared. So our b value is 2. All right, so to convert this to complex form, we would have the quantity x plus 2i times the quantity x minus 2i. And that's it. We just factored it into complex form. Okay, so most of the time we're not, like, you're going to be seeing that more, like seeing this less often than just factoring the patterns. Okay, then next up, let me go ahead and erase and move on up because we're going to want this next information for example 6. The powers of I can be easily simplified using the pattern below. Okay, so let's look. I to the power of 1 equals I. Okay, great. I squared equals -1, which we know. I cubed is equal to I squared times I, but we know I squared is -1, so that equals a negative I. I to the 4th is equal to I squared, which is equal to -1, times I squared, which is equal to -1. So -1 times -1 equals a +1. So we've got this really cool pattern. I, -1, -I, +1. Then it keeps going and starts to repeat itself. I to the 5th equals I to the 4th, which we just discovered is 1 times I, so it's equal to I. Then I to the 6th is equal to I to the 4th, which is 1, times I squared, which is -1. So now we have a -1. I to the 7th is I to the 4th, which is 1, times I cubed, which is So I to the fourth was 1. I cubed we saw was negative I. So 1 times negative I is negative I. And it keeps repeating. It says, and so on. So the fun thing about this is, or the helpful thing, is that to simplify large powers of I, divide the exponent by 4, because that's the number that it takes to repeat. Okay, this is the number of different values before the pattern starts repeating. The remainder will give a power of I equivalent to the original power. Okay, so what it's saying is we're taking out, when we're dividing it by 4 here, we're taking out groups of 4 or groups of I to the power of 4, which are all equal to a positive 1. And we know that 1 times 1 times 1 times anything is this number that we multiply. So if we multiply it by I, if we multiply it by negative I, or if we multiply it by negative 1, we're going to get an equivalent answer. So let's do this here on example 6. We're going to simplify I to the 59th power. All right, so we're going to take the exponent, 59, and we're going to divide it by 4. What's 59 divided by 4 equal? Or you could do it out this way, right? Might be easier to see 59 divided by 4. 4 goes into 5 once, and we subtract 4, and we have 1, and we bring down the 9. 4 goes into 19 4 times, we subtract 16, and we have 3 left over. Okay, so these 14s doesn't even matter, okay? Because what this is saying is it's saying I to the 59 is equal to I to the 4th power times 14. Okay, there's 14 groups of those. Plus a 3 here, right? We have that remainder of 3. Which, what that really means, okay, I'm going to rewrite this, is that it's I to the 4th times the 14th power, but also I to the 3rd. That's what we're getting at, because these all equal 1. It's just I to the 4th is 1. 1 to the 14th power is still 1. Okay, but I to the 3rd, we know, is equal to negative I. So I to the 14th power, or sorry, 1 to the 14th power is 1 times negative I is negative I. So I to the negative 59th, or sorry, I to the 59th power is equal to negative I. I know it kind of took a long way to describe that and get there. I'm sure that you will understand it quicker than it took me to explain it. Okay, have a good one, and I will see you.